Okay, welcome to StudyOrgo's explanation of addition of bromine across alkenes. So to start the reaction, we'll take an alkene, in this case 1-methyl cyclohexene, and react that with diatomic bromine, which is dissolved in a nonpolar organic chemistry solvent, methylene dichloride. And this is going to lead to the alkane product that has 2 bromines added across the original double bond. So to go over the mechanism of this, the reaction is initiated by the pi bond electrons that originated from the alkene. So the alkene is going to attack the diatomic bromine, and this is going to break the sigma bond between the 2 bromine atoms to form a carbocation intermediate located down here. The carbocation can be drawn on either carbon number 1 or carbon number 2, depending on how you draw the attack on the bromine by the alkene in the original model. So depending on which one you start with, you will end up with either a positive charge on carbon number 1 in this case, or carbon number 2. But a common resonance stabilized intermediate that's required for the mechanism on exams is the formation of the Bromonium Ion Intermediate. And this intermediate exists because having a positive charge on carbon is very unstable. And because bromine is electronegative, it has lone pair electrons around it. And so we can resonance stabilize this carbocation line structure here by making another bond from bromine using its lone pair electrons to stabilize the charge on carbons and make another bond to the bromine. This places the positive charge now on bromine. And while both of these structures are very unstable, the fact that both of them can exist induces a stability known as resonance stabilization. And this allows the mechanism to proceed much more rapidly. So it's in fact the bromonium ion intermediate that's going to lead to the product. So bromonium ions are going to be very similar to carbocations in that they're sp2 hybridized, and that means that they're planar and trigonal in geometry. So attack by the negative charge bromine anion can occur on either the front of the bromonium ion intermediate or on the back of the bromonium ion intermediate. And this is going to lead to formation of 2 possible outcomes. The original bromine that was attacked by the alkene will kick off. In this case, if the bromine anion attacks at carbon number 1, that'll leave the original bromine on carbon number 2, and this leads to our first product. If bromine anion attacks on the carbon number 2, this will now force the original bromine to add to carbon number 1, and we get the second product. So let's go over some tips about how to make sure that you get the mechanism right. And there are really 3 major tips. And the first one is going to be in addition to the stereoselectivity. So a key aspect of this reaction is that the stereoselectivity of the reaction is anti. That means that both bromines are going to add on the opposite side, the opposite face of the original alkene. So in this case, we have a bromine that is wedged and a bromine that's dashed. What that means is that they're on opposite sides of the ring. If we look at the other product, it's exactly the same product except in reverse. And that is that in this case, carbon number 2 now has the dashed and carbon number 1 has the bold. The reference in this case is the methyl. So the methyl was originally sp2 hybridized. That carbon is now sp3 hybridized. So the methyl has the choice of either being bolded or wedged. And in either case, that'll lead to formation of a mixture of products that will have both stereoselectivity. The second major hint for this mechanism is going to be the formation of the Bromonium Ion Intermediate. If you do not write this down on the exam, you will lose major points because it's the bromonium ion that's attacked in either when it attacks the bromine anion attacks at carbon number 1 or carbon number 2. This leads to a common intermediate that explains how you get both products. And the third one is this mixture of products, and this is going to refer to an enantiomeric formation of the product. And in this case, we're going to see a racemic mixture. And that's because in the bromonium ion intermediate structure here, it is equally probable that the bromine will attack from the front or from the back at carbon number 1 or carbon number 2. And this is going to lead to both of these products being formed in equal amounts. And this is how we describe a racemic mixture. Remember that racemic mixtures are what we call optically inactive, and that is because both enantiomers are in the same solution, in the same concentration, that the use of plain polarized light in a polarimeter to detect which enantiomer you have is canceled out by the other. This leads to an optical activity of 0. And so therefore, the racemic mixtures are not detectable by polarimetry to determine the enantiomeric ratio because it's equal. And so with that, we'd like to thank you for watching this organic chemistry mechanism explanation by StudyOrgo.